Okay, our last topic for this chapter is about heat energy and chemical reactions. So chemical reactions involve changes in energy. And the energy of a reaction is an extensive property, which means that it depends on how much stuff we have. Okay, so if I'm, for example, burning of wood, that's an exothermic process that releases heat, right? If I burn one log, I get a certain amount of heat. If I burn 10 logs, I get 10 times as much heat. Okay, so the energy of a reaction depends on how much material you have. Okay, and what we're going to be dealing with most is what's called a fuel value. Okay, and a fuel value is the amount of energy that can be produced by the combustion of a material. Okay, and we have a variety of different sort of fuels here on this table. Methane, natural gas, propane, stuff like that. You can also put food on this list because what's happening inside your body is breaking down of that material and it releases energy. And you can determine a fuel value for food because a fuel value is just energy per mass, kilojoules per gram. So we could talk about the amount of energy that you get from 5 grams of apples or 5 grams of potato chips or whatever, and it would be a fuel value in kilojoules per gram. Okay, and we do these types of reactions in a bomb calorimeter, right? Most of our previous examples were in coffee cup calorimeters. Okay, and these we're going to be talking about what happens inside a bomb calorimeter. And even though the mechanism of a bomb calorimeter is more complex than a coffee cup calorimeter, the equations and problems you'll be doing are actually quite a bit simpler. Okay, so let's see how much energy in kilojoules would be released by the combustion of 0.5 kilograms of butane gas. Okay, so our fuel value for butane is right here. It's 49.5 kilojoules per gram. Okay, so I've said this before and I'll say it for the rest of the semester, but anytime you have a fraction like this, so a something per something, that's a conversion factor. Okay, so I can also write this as for every 1 gram, I get 49.5 kilojoules. Okay, so either way works. Okay, so I'm given information in mass, 0.5 kilograms. Okay, so if I convert that to grams, I can use one of my fuel value conversions to give me energy. Okay, so let's set that problem up. We're going to start with our given information, 0.5 kilograms. So I'm going to convert that to grams. And there's 10 to the 3 grams in 1 kilogram. Okay, so that converts my kilograms to grams. So now I've got grams on top here. So if I cancel out my kilograms. So I want to write my conversion factor with grams on the bottom. 49.5 kilojoules per gram. Okay, so we're going to find that that gives us, to 2 sig figs, 2.5 times 10 to the 4 kilojoules of energy. Okay, so we use fuel values as conversion factors. Okay, so it's not a new concept, we're just putting some different units on there. But using it as a conversion factor to go between energy and mass is what we're after. So let's try another one. Methane has a formula of CH4. How much heat is released by the combustion of 1 mole of methane? So our fuel value for methane is right here. So 55.5 kilojoules per gram. okay? But our units are in grams. But it's a good thing that we already know how to go between moles and grams, don't we? Okay, so the molar mass of methane, of CH4, is 4 times the mass of a hydrogen, so 4 times 1.01, plus 12.01, which is the mass of a carbon. So the molar mass of CH4, let's write CH4, is 16.05 grams per mole. Okay, so if I've got 1 mole, I can convert that to grams. Now that I'm in grams, I can use my fuel value as a conversion factor, and I'm going to want to put grams on the bottom. All right, so when we do that calculation, we get a total of 891 kilojoules. All right, now our last topic is a thing called enthalpy, okay, and it's related to heat. All right, so what this diagram is showing is that depending on which process we're talking about, melting and freezing have the same energy involved, but different sign. Notice that the energy on one of these, on freezing, is negative, and on the melting is positive. So if I have a block of ice, and I freeze it, or excuse me, I've already got a block of ice. If I've got a block of ice and I melt it, okay, that means that I have to put energy in, right? So melting is endothermic. Okay, I have to put energy in order to melt something. I have to heat it up, okay? And the amount of energy that it takes is 6.01 kilojoules. Okay, but now I've got liquid water. So if I want to freeze that liquid water, I have to take energy out. Freezing is exothermic. Okay, because we're taking energy out, we're cooling it down. Okay, and the point is that the amount of energy that it takes has the same magnitude, right? 6.01 kilojoules, whether I'm melting or freezing. The difference is the sign. That negative sign tells me which direction the heat is going. Is the heat going in or going out? Okay, so opposite processes have the same magnitude but opposite sign. Okay, so let's look at our last slide here. So magnesium carbonate decomposes to magnesium oxide and carbon dioxide gas with the absorption of 100.7 kilojoules per mole of magnesium carbonate. Write a balanced chemical reaction including the reaction enthalpy. Okay, so let's start with the reaction part. Okay, so it says magnesium carbonate decomposes. So the formula for magnesium carbonate, MgCO3, remember because we have magnesium 2 plus and carbonate 2 minus, so they go together 1 to 1. And it says that it decomposes, so it doesn't react with anything, it just breaks apart. And it breaks apart into magnesium oxide and carbon dioxide gas. Okay, and then it says that it absorbs 100.7 kilojoules per mole of magnesium carbonate. Okay, so if it's absorbing energy, that means that energy is going in. Right, so our enthalpy, which is how much heat is going in, so the delta H is a positive 100.7. Okay, so this idea of an entire reaction And the energy associated with that reaction we can write as a delta H on the outside. Okay, and depending on whether it's releasing or absorbing energy, we'll make it either a positive or negative value. Energy going in or energy coming out. And that's going to do it for our Chapter 8 lecture videos. I hope it's been informative and useful, and we'll see you in our next Zoom meeting.